Welcome to ECE 320 Electronics 1, lecture number 24, CMOS Logic. Now, what we've looked at before is TTL logic and DTL logic. DTL logic is diode transistor logic. That was used back in the 60s. It's the first form of logic, and it has problems. Those diodes inherently have capacitance, which limits the maximum speed. TTL logic is much improved over DTL logic. However, it still has its limitations. First, the input impedance is not infinity. That limits the fan out. The corresponding power consumption is somewhat high. If it's 5 milliwatts per gate and you have a million gates, you're talking about 5 kilowatts being dissipated in one chip. The maximum clock frequency is also limited. DTL logic is limited to about 1 megahertz, TTL to about 10 megahertz. CMOS logic avoids these problems. To illustrate that, let's assume I've got a CMOS device that turns on at 5 volts, and the resistance at 5 volts is 1 ohm. First, let's build an inverter. One way to do that is use a switch, like we talked about in our last lecture. Have an N-channel MOSFET as a switch. I'll turn on and off a 1K resistor. When A is 0 volts, this is open, and I get 5 volts out. When A is 5 volts, this becomes 1 ohm, and I get 0 volts out, or 0.005 ohm, or volts. Problem with this design is I still dissipate 5 milliamps when the switch is on. Well, I can do the same thing on the high side. On the high side, if I use a P-channel MOSFET, then what happens is when A is 5 volts, VGS is 0, the switch is off, and Y is tied to ground. When A is 5 volts, actually when A is 0 volts, I've got VG is 0, VS is 5, VGS is minus 5. At minus 5 volts, that creates a P-channel, and current flows. If this is 1 ohm when it turns on, then I've got Y is pulled high, and it's going to be 4.995 volts, essentially 5 volts. Again, the problem here, though, is that when the switch is on, I am dissipating 5 milliamps. The way MOSFET inverters are actually built is put the two together. I have a P-channel on the high side, N-channel on the low side. When A is 5 volts, the N-channel MOSFET turns on, and Y is pulled to ground. When A is 0 volts, the P-channel MOSFET turns on, and Y is pulled high. The advantage of this is at any given time, one of the two MOSFETs is off, so the current draw is 0. This is way better than TTL or DTL logic. It uses no power to maintain its state. In addition, ideally there's no current flow. This is a capacitor, the current flow coming in is 0, so I can sit there and maintain a voltage with 0 current. That's something TTL, DTL can't do. If you simulate it, it's also much faster. This is a Circuit Lab simulation. The MOSFETs I found in Circuit Lab are complete overkill. These are capable of 12 amps and 100 volts. All I need is basically 5 microamps and 5 volts. If I chose a smaller MOSFET, it would actually have smaller capacitance and much quicker speed. But even at this, completely absurd overkill, it's still capable of 100 megahertz or 80 megahertz for the MOSFET. Like DTL and TTL logic, I get current spikes. When I have a transition from logic 0 to logic 1, what happens is momentarily both MOSFETs are turned on, and they get current flow from power to ground. Once the MOSFETs stabilize, one of them is turned off, the current flow goes to 0. So the steady state current flow is 0 for MOSFET, unlike DTL or TTL. However, it's the transitions is when I use current. What that means is for computers built with CMOS logic, which is pretty much everything, the current is proportional to clock speed. The more I switch, the more current I draw, and it's only at the switching times when I'm actually drawing current. That was for a CMOS inverter. I can also build AND gates and OR gates. So let's start with a NOR gate. For a NOR gate, if I put these in parallel, I want to build a NOR gate, so Y bar is A or B or C. Y is A bar or B bar or C bar. Kind of note this is Y bar. If these transistors are turned on or MOSFETs are turned on, any of them are turned on, Y is pulled low. So Y is false, Y bar. If A is true, or B is true, or C is true. I can do that on the high side. On the high side, I use De Morgan's theorem. If y bar is A or B or C, y is not A or B or C. Using De Morgan's theorem, it's A bar and B bar and C bar. On the high side, if this is true, these are turned on, y is pulled high. So that'd be series. And is series. And here you have a double negative. I want to apply A bar when this is turned on, but for P-channel MOSFETs, 0 volts is actually on, 5 volts is off. So I automatically get that not function. Put the two together, and the low side are the 3 MOSFETs, N-channel MOSFETs in parallel. High side, the 3 are in series, and that's De Morgan's theorem. Series goes to parallel. This would be a 3-input NOR gate using CMOS technology. I can do the same thing with a NAND gate. For a NAND gate, I want y bar to be A and B and C. So y is pulled low, if A is on, and B is on, and C is on. So and is series. Using De Morgan's theorem, and becomes or, series becomes parallel. Y is not A, or not B, or not C. And that's what you have here. Not A, 0 volts actually turns this on. 0 volts turns on this one. 0 volts turns that one on. This is the high side. There's the low side. Again, they're related by De Morgan's theorem. Series becomes parallel. So that's a 3-input NAND gate. The cute thing about CMOS technology is you don't really have to use NAND gates or NOR gates. You can actually implement logic in a single shot. Just have to note that AND means series, OR means parallel, and the high side and low side are related by De Morgan's theorem. So for example, suppose I want to build y is A bar, B bar, or C bar. Then this is actually the high side. Y is series is AND, A bar and B bar. Parallel is OR, and parallel with C. So there's the high side. The low side is De Morgan's theorem. Series becomes parallel, A or B. Parallel becomes series. So this is a CMOS gate to implement y equals A bar, B bar, or C bar. And note I didn't have to use Carnot maps or do a couple of NANDs and NORs together. I did in one shot. That's another huge advantage of CMOS technology. It's faster, lower power consumption, uses fewer gates. I can do the logic all in one shot. Takes less area than actually the silicon, at the silicon level. That's pretty much how all computers are built, using CMOS technology. So that's lecture number 24 for ECE 320, Electronics 1.